Hi, this is Gordon Parker from Michigan Tech, and in this video we'll make a model of a double pendulum where the lower pendulum is much less mass than the upper one, and of course we'll use SimMechanics. The motivating question for the example is, can we completely neglect that lower pendulum? Now we're not really going to answer this question, but we're going to see some ways to gauge how much the lower pendulum distorts a single simple pendulum approximation. Now I've mentioned before that I don't like to rely on a single analysis method to draw any conclusions. That is, it's always good to have a way to double check your results, especially of a simulation. We're going to do some of this today by comparing the SimMechanic results to an ideal large angle simple pendulum implemented using core Simulink blocks, that is, no SimMechanics. I'll also compare the double pendulum model to a ghost model of a simple pendulum to see the differences during simulation. That is, you can see the differences via the animation. This can be a good trick to incrementally develop complicated SimMechanics models. But first, I'll sketch out the double pendulum system and list out all the mass properties and lengths, etc. that will be needed for the SimMechanics model. So here we go. We have the first upper rod and sphere. Then attached to it is this appendage, another rod and sphere that hopefully will be somewhat negligible compared to that upper pendulum. We'll label all the bodies, 1, 2, 3, 4. The upper pin is 0, and define an angle theta for that first pendulum. Now each one of these bodies has mass properties and lengths associated with it. So for the links, it'd be rho, a density, r, a radius, and an L for a length. And for the spheres, it's just a density and a radius. And then those generate masses, volumes, and inertias. Now for the upper body, the upper link I should say, we'll make that out of aluminum, so 2,700 kilograms per meter cubed for the density. And a rather small radius, it's a cylinder, and a length of 24 centimeters. That first ball is stainless steel, so quite heavy, 7,800 kilograms per meter cubed, and a much larger radius. And bodies 3 and 4 are going to be quote-unquote light, and perhaps they'll be negligible, but we'll see their effect when we get into SimMechanics. Now all these properties can be used to generate masses, volumes, and inertias. And so for the link, notice that I'll use an inertia that does not assume a slender rod, so it'll take into consider its radius and its length. And certainly we'll do that for all these components, and we actually don't have to do anything. SimMechanics will sort all that out for us. But just be aware that it's actually using these non-approximate values for inertias. So let's look at this system again so that we can get down to a simplified model of it that we'll use for comparing what SimMechanics generates. So we'll annotate this version of the diagram with a couple lengths. So there's L1 and there's our R2, the radius of that first sphere. And again, that's 0.0 up there. And we'll see if that rod, that aluminum rod, can be considered massless compared to the stainless steel ball that it's attached to. Now this is a conservative system, so we could certainly use the fact that the total mechanical energy is conserved, or that E dot is 0, in generating some simplified equations. Or we could use F equals ma, and the sum of the moments about point O is equal to the inertia about O times theta double dot. And that's what we'll use to generate a model. So here's a free body diagram with the reaction forces at the pin. And this total distance is L1 plus R2. And we'll need that for computing the moment about O. So the moment about O is just equal to, well, m2, the mass of the sphere, times g times that distance times sine theta. Now I should have annotated that free body diagram with an mg coming straight down from the center of mass. Now JO is equal to J2, which we've already calculated for the sphere, plus, using the parallel axis theorem, the additional L1 plus R2 squared component. So there we have that. And now we can just write out the equation of motion for theta using m0 equals j0 theta double dot. So I'll just copy back down our j0 where I've substituted in j2 and multiply that by theta double dot. And a few things cancel. Well, actually just the m2's cancel, the masses. That's kind of nice. So we get rid of that and write out a final version of the equation of motion that we can just box. So we'll use this in checking some of the SimMechanics results in just a minute. Let's play around with this a little bit more so that we see how we'll implement this in Simulink and have that model running parallel with our SimMechanics model. So here's another version of that boxed equation where I've just singled out the theta double dot. And here's how we'll implement that in Simulink. Notice that if I have theta double dot, I can integrate that and get theta dot, integrate it again and get theta. Once I have theta, I can take the sine of it and then multiply it by a gain, which is everything else in this upper piece right here. And that, lo and behold, is theta double dot. So that's exactly how we'll implement that in Simulink. And just to get it down on paper, our negative k that we'll have to code into Simulink is this big expression. Now this is an idealized version of our system, right? It assumes that that upper link's mass is 0. So there's no body 1 essentially. And it also, there is nothing hanging from that stainless steel sphere. So now how do we put this into SimMechanics? Well, let's draw it one more time. So here is our upper link and sphere again. And we're going to want to rotate about that pin by theta, which is the angle here. And we'll make this, we'll use, I should say, a revolute joint from the SimMechanics palette. And then these items here will be solids, again from a SimMechanics vocabulary. Now they sort of have a world frame bias, and I'll explain what that means in just a minute. But here's the world frame that will be given when we fire up SimMechanics. And the other thing that we need to take into consideration is that we'll have a gravity vector, and we'll just put that in negative z. So what we'll do in SimMechanics is we'll rotate 90 degrees about x of the world frame. So here's our world frame again. Rotate that 90 degrees about x, and it points y up and z out of the page. So now we have a perfect place to put our revolute joint. Keep in mind that revolute joints are always in the z direction. So we had to convert or rotate our world frame into an orientation such that we could attach a revolute joint that was in that z frame. Now here's what I mean about the solids and the world frame bias. So if you make a cylinder, it's always going to have z pointing up through that upper. And so what we'll do is we'll rotate 90 degrees about that frame to get it back to z pointing back up again. And then we can attach solids to it. We could attach a cylinder for that upper link and then attach to it the sphere. Of course, we'll have to do some z-axis translations to make all that work, but that's just a little bit of detailing. Okay, so SM new once again, and I'm going to get rid of this graphical way to access the blocks. And let's stretch this out a bit because we're going to need a lot of room for this particular model. Here's the browser we'll use to grab some blocks. And there's our MATLAB window, just sort of cleaning things up a bit. Let's go ahead and change this. It defaults with this value of acceleration due to gravity. I'll just change that to 9.81. Keep it in the z direction. Let's fix up the integration method. We'll just set that maximum time step to 1/60 just so that the animation looks a little bit smoother, more pleasing to the eye. And we'll leave the default integration method alone. Might as well start getting in the habit of saving this thing. We'll just call it pendulum example would do. Okay, now we can start getting down to business here. So the first thing we need to do, based on the notes that we had before, is make a rotation about the positive x-axis. Now I'm going to use red for rotations for these transform blocks and blue for translations. And as always, I'm going to grab some tokens from the block annotation area so that we can see on the front face of the model what the heck we're doing with these rotations and translations. I'll only have to do this a couple times because then I'll just right click and drag blocks to copy them, and I won't have to go through all this token business. Okay, so we'll go into here. We've done this before in some of the other videos. Pick standard axes, 90 degrees, about the plus x. Boom, there we go. So we're making our way. We're not going to worry about the solid just yet. Let's attach this, and how about we clean this up a little bit? We'll just grab this thing. It'll ask us if we want to create a subsystem. Yes, we do. And we'll name it, name it config. And we'll go inside it, left click, and might as well just call the output port world so that we remember it's the world frame. Wonderful. Okay, so let's go into Simscape second generation, and we'll grab a joint. We're going to grab a revolute joint. Has a lot of the same properties as a prismatic joint. We could add stiffness and damping, but we're not going to do that. We're just going to use it as a straight up rotation about the z-axis. Let's go ahead and allow us to set the initial rotation angle of this thing, and I'll set it to 70, some nice big angle that we can see. And let's go ahead and also, well, you can see we can do actuation, but we're not going to actuate it. We'll just let it swing freely. But let's go ahead and put a sensor on position so that we can see the rotation angle. And let's also look at some forces. We'll look at these constraint forces at the pin. There we go. So we have a couple extra ports. And connect this up. Beautiful. And of course we go into block annotation and add some information so that we can see what that initial condition of 70 degrees is on the front face of the model. That'll just make it a little bit easier. Notice that I'm just going to type in the values of everything into this model. I wouldn't normally do that. I would use a .m file to configure it, but for the purposes here, I think that's sufficient. You can jazz it up as you see fit using some of the concepts in the other videos. Okay, so let's set this up so that our sensor outputs, the position and the forces, can be brought into scopes into Simulink. So I'll have to use this PS to S converter. I'll get rid of the name on it because I can see what it is. And right click drag. And we'll use this go to from strategy that I used in maybe video 3 or 4. Just lets us clean up the block diagram a bit. Now the output position is in radians, so we'll need to convert that into degrees. Well, we don't have to, but it's kind of nice. So there we have that. And now let's do the go-to from business. So there's a go-to block. Here's a from. And I like to make them a little bit skinnier just so I can cram more stuff into the block. And there we go. So we'll call this SS Ang for Simscape angle. I don't know. It's as good a name as any, I guess. Scrunch that in a bit. And we'll do the same thing here. I'll just use a scope instead. There we go. And let's give this a proper name. I'm going to call this B-rod because what I'm going to do is I'll use blue for the upper pendulum and I'll use yellow for the lower pendulum. So B for blue and Y for yellow in naming things. Consider of a nice descriptive name on that reaction. And here we go. Here's our next rotation. So remember from the work I did sketching that we have to do this next rotation, which is a rotation of 90 degrees about the negative x. So we need to stretch things out a bit so that we can see everything. And once we have that rotation done, then we can start attaching solids to it. Now the first solid that we're going to attach is actually a cylinder, and it'll attach its center to the rigid transform. And so I need to shift down in the z direction by half the length of that cylinder. And remember, the upper rod was of length 24 centimeters. So I'll just call that 24 over 2, just so I kind of remember where I came up with that number. And now I've shifted or created a new frame that shifted down from the pin by 12 centimeters. Now I need to change these annotations a little bit because they are translations and not rotations. So let me fix that up. Grab some appropriate tokens. There we go. And now we can start attaching some solids to it. Okay, so this thing we want to make a cylinder, and we'll make it a blue cylinder, or bluish at least, and it should be 24 centimeters long, based on what we did before, with a radius of 1 centimeter. Okay, so, and the density was aluminum, so 2,700 kilograms per meter cubed, and we'll make it blue. Kind of a light blue. I'll use dark blue for the stainless steel sphere. And give it an opacity of half. It's always good to have the opacity kind of ratcheted down a little bit, so that way when you're connecting things up, you can see if you have some interferences. Okay, and I'm going to Control R to flip it around a bit. Scooch it up here. And let me change the color. Remember I said I was going to use blue for translations and red for rotations. There we go. And yeah, I should call this a translation. There. And let me give this a descriptive name. So we're going from the blue, the B rod pin, to the center of the sphere. Right to that point. There's our upper pin, and there's the center of the sphere. And it'd be half of the 24 centimeters. There we go. So now we have a pendulum all ready to go. And now I'm going to make that pendulum a little bit more interesting by attaching a stainless steel sphere to the bottom of it. So B sphere for blue sphere. And let's make it a sphere. And let's see, a radius of 6 centimeters. And the density, we're going to use stainless steel, so 7,800 kilograms per meter cubed. And let's make it a little bit darker blue. Oh yeah, there's a good blue. I can hit F5. Ah, there it is. Nice looking sphere. No, I can't just attach it. I need to shift that down a little bit from the center of the rod. So let's give this a descriptive name. It's going to be the blue rod center to the sphere center. Okay. just attach this. Now notice I haven't changed anything in that transform yet, but let's just look at it to see what happens, and that will give us a guide in terms of how we should set the value of that transform. So save it, update the diagram, and look at that. You can see that interference because of the opacity, and you can see that what we need to do is shift that down also by the radius of the sphere. No big surprise. So if we go to here, we need to do 24 divided by 2 plus 6 for the radius of the sphere. Update the diagram. Let's take a peek at it. Ah, beautiful. So now no more interference. Well, now let's build up that Simulink version of the simplified model. So grab an integrator. You can right click and drag. Make some copies of it. And remember, this model is going to neglect the mass of that upper rod. So it's not quite going to emulate what we have in SimMechanics, but it'll be close. And you'll see in a moment how we can actually compare the two on equal footing. So there's our negative gain, where we'll have to type in some long-winded expression. And let's see here, we need a trig function for the sine. Oh, look at that, it defaults to sine. How nice that is. Control R a couple times to flip it around and connect it up. Beautiful. There it is, just like in the hand drawing. And now we have to type in this big expression that we had in those hand notes. Kind of a long-winded affair. Divide by 100 so that I can put things in centimeters. Everything here, of course, has to be in meters. I can enter it in centimeters, but I have to make sure that I have the scaling back to meters. Okay. And let's see, the output of this will be in radians, so we'll want to be able to see that in degrees. And of course, we'll want to see that on a scope. Yes, that is a scope. Right click drag to make a copy of it. And there we go. I'm going to break this link because we want to actually look at the output of SimMechanics and this Simulink version of the model. So let me grab a multiplexer or a mux block. Okay, so the Simulink version of the output will be the second channel, which will be red on the scope. The first channel, and I'll just use this from block, will be in yellow. So update the tags, grab that one, and boom. So we have a nice little pendulum on the left, nice Simulink model on the lower right, and we can just run it. Pretty exciting. So there's a pendulum. Let's scoot it back a little bit so that we can see the whole thing. Wow, look at that. Turn on the frames. It's always good to have frames on. Gets a little bit busy, but then you can see better how things are moving around. It's always good to be able to click on your frames and get a sense of where everything is. So here's our B-sphere frame. There's the base and the follower frame of that translation. Here's our rotation, base and follower at the pin. It's always good to explore the frames a little bit. But let's take a look at this. So let's see, we have 0 on one of the channels. Oh, I thought it was going to be red, but it's actually blue for the second channel. And that is because we didn't, or I didn't, set the initial conditions for these integrators. Now for the first integrator to go from acceleration to velocity, the initial condition should be 0. But that second integrator should have an initial condition that's consistent with the Simscape model, or the SimMechanics model, which was 70 degrees. So let's fix that up. And it has to be in radians, so there we go. Beautiful. Boom. Now that should get rid of our boring second channel of that plot. Just can't get enough of that swinging around of the pendulum. But really, this is what we want to see. Now, we can see here there's a little bit of deviation between the yellow, which was the SimMechanics model, and the blue, which was our Simulink model. And that's because the Simulink model ignored the mass of that rod. Or at least that's what I'm postulating. So let's check that. We'll just go into here, which is our rod solid, and yeah, let me first fix it up with the block annotation parameter so that we can see what we have for the density and the length and the radius of that rod. And then we'll play around with those parameters a bit, basically zero out the density and see if we then get a match between the SimMechanics and the Simulink model. Now, be warned, you can't always just run around setting densities to 0 in SimMechanics models, otherwise you'll get some horrible errors, degenerate blocks, and things of that nature. And one of the main reasons for that is that you can't have 0 mass between two different joints. Now that isn't the case that we will have here. We have just one joint, and we have actually 2 solids attached to it. So making one of them 0 mass is actually okay. So let me fix up the sphere block annotation properties also while I'm at it. Okay, some radius and some units, and the old density. Okay, so now let's go into this one and zero out that density. I'll just multiply it by 0. And the reason for not just setting it to 0 is because in my stage in life I might forget what the original density was. But this way I won't forget because I can actually see it. So we run it. Boom. And check this out. Oh, look at that. A perfect match between the yellow Simscape version and the blue Simulink version. So what this tells us is that we've likely implemented both models in the same way and hopefully correctly. Again, it's always good to have multiple ways to check what you're doing in SimMechanics or any simulation. So let's get our rod back up to aluminum, and great. So the next thing we want to do is add on that compound pendulum, or I should say that double pendulum. And so let me do a little bit of rearranging to get ready for that. Because what I'm going to do is scrunch everything down, and then I'm going to segregate it so that I can grab everything from that joint backward, and then just right click and drag and make a copy of it and color things yellow and change some lengths and so on, and then we'll have our double pendulum. Remember at this point that last frame, that last blue frame, is actually in the same direction as the world frame. So we have to do this rotation again where we rotate it 90 degrees about the plus x-axis. And of course we'll have to translate down to the bottom of the sphere to attach that second joint. So here's our translation. Give it a descriptive name. So the B sphere center to the B-sphere bottom. Now, which axis should I rotate about? I honestly don't remember. So I'm just going to leave it the way we have it and then do an update diagram, and we'll sort it out that way. And that's a good way to use the update diagram and the graphics to figure out what it is you should do as you're building a model. So let's take a look at that. And look what's happened. So we have this new axes, but it's in the wrong spot. It really needs to be down from the cyan one that I've just highlighted, and you see it's off to the right. So I need to go in the Y direction, not the Z direction, to offset that second translation, and actually the negative Y direction. So I'll just go in here, flip this around to a negative Y, and check it again. Haha, beautiful. So that's the point that we'll attach the second pendulum to. And the Z-axis is pointing in the right direction. Wonderful. So let me do a little bit more scrunching so I can cram a lot into this little tiny window. And here we go. So I'm going to grab all this stuff, right-click, drag, and boom, I now have a double pendulum. Wonderfully easy. Let me fix up some of these names. And we'll use yellow, as I mentioned before, for the second pendulum, so I'll use a Y in front of everything. Now, let's make this the second pendulum a little bit different. I really didn't say anything about it in the handwritten work, but let's make it twice as long. We'll make it 48 centimeters, and we'll make it really skinny. How about 0.2 centimeters for the radius? So a long, skinny, lightweight second pendulum. So let's see, right now we're set to aluminum. Let's see here. So we'll make this yellow. And let's just make it 1,000. Something much lighter than aluminum. So 1,000 kilograms per meter cubed for the density. And so for this transform, I'll have to adjust it for the longer length. So 48 divided by 2. So I can get rid of this. And let me fix up the sphere. So we'll make it small, so 3 centimeters. And again, 1,000, some lightweight thingy. And we'll make it a dark yellow. But still with opacity of 0.5 so that we can see any sort of interference if there are any. And let me fix up this tag. Let's call it 2. Update the diagram. Ah, great. Oh, but it's pointing in the wrong direction. It's at the right spot. It's attached to the right spot, but it's pointing off quite a bit from what it should be. It should be hanging straight down if we wanted to keep it in a kind of an equilibrium position. And the reason is that when I copied over this joint, I left its initial condition at 70 degrees. Well, because this joint is relative to the first one, it should really be negative 70 degrees if I want that second pendulum to be hanging straight down. Oh, there we go. Perfect. So it's as if we're holding the first pendulum at 70 degrees, that other appendage is hanging straight down, and then we release it and get some interesting motion. So let me add another signal to our output scope. I'll just throw in there the second pendulum's angle. It's really not useful to compare to the first pendulum's angle, but it's telling us something about what the second pendulum is doing. Update the tags. Pick this. Boom. So there we have a fairly heavy first pendulum, a very light second pendulum. And let's get some names on here. Okay, update the diagram. There it is. Looks good. Let's run it. Oh, look at that motion. Some crazy stuff with that second pendulum. But the question is that really affecting the upper pendulum? It's kind of hard to tell from looking at this animation. But if we look at the scope, we can see the wild red of the second pendulum, but the approximate Simulink model looks pretty much like the Simscape model. So really that lightweight pendulum didn't have a whole lot of effect on the upper heavy pendulum. Now whether or not that's too much, that's depends on the application. But it's just to illustrate how you can look at sort of what you might normally consider second order effects and then play around with how much they could affect the core simulation. Now we're going to do one more thing here. Sometimes you don't have the ability to easily create that Simulink model. So let's just look at a different way to double check what we have with the Simscape approach. So what I'm going to do is first just sort of segregate a couple pieces. That I just put a blue box around the first pendulum. And let me move this over a little bit. And I'll put another blue box around this pendulum. And let me stretch it out a bit. And name it. I guess I should have annotated that other blue box, but you get the idea. This is a nice way to clean up the model just a little bit. Okay. Now let's grab this whole thing and just right click and drag and make a copy of it. And this is where we'll make what I would call kind of a ghost model. I'm just replicating that first pendulum. Let me scoot things around a bit. I know it's really tiny right now, but I'm going to try to cram things together. And by hitting the space bar and fitting everything to the screen, I can maybe be able to see everything at once. Okay, so now I'm going to take this first link and just get rid of it. I could have set the mass to 0, or I could just comment it out. Either way is good. I kind of like commenting it out, actually, because then I'm not running into the potential risk of setting a mass equal to 0, which can wreak havoc, as I mentioned before. Okay, and what this will let us do is see superimposed onto the blue pendulum another pendulum, which I'll make green. So I'll just go ahead and make this ball green now. And then we can visually see the difference between an approximation of the upper pendulum, where I've set I neglected that upper link, and compare that visually to the true unapproximated upper blue pendulum. So I'll call this tag approximate. Well, I need to attach it after that first rotation. There we go. Now everything is good. And we can run it. And what you should watch for is a difference between blue and green in that upper pendulum. You can see it now. So you can see the deviation. There we go, freeze it. You can see a little deviation visually between the blue and the green. Now this is one way you could go after it if you didn't want to create an approximate model using Simulink. And of course we could take the outputs of this thing and feed them into our scope, just like we did the Simulink model. Let me scoot this around. And just so you can see that these are all the same, I'll just bring in that approximate signal in here. Remember, this is where we had that red second pendulum angle. Now I'll just bring in this approximate angle from the ghost model, and we can run it again and look at it on the scope and see the differences. So again, the idea here is that if we didn't have that Simulink model with the two integrators and we just wanted to compare the effects of with and without that upper rod mass, we could do it strictly in Simscape. And you saw the differences there. As we saw before, they're not too extreme. Now let's go ahead and make that lower pendulum just a little bit more massive. I'm going to make it out of aluminum now. So instead of 1,000 kilograms per meter cubed, we'll make it 2,700 for both the rod and the sphere. And let's see how this looks in Simscape. Update the diagram. Keep an eye on the yellow or the green and the blue and the crazy motion of that yellow pendulum. You can see almost 180 degrees out of phase of the green and the blue. The yellow's going wild. Lots of good stuff there. And we can go down here and look at it on the scope. And you can see the red is now that approximate model, and it's just doing its normal sine wave thing. The yellow is the Simscape, and you can see some pretty significant distortions there with the heavier second pendulum. So there you go. Finally something other than a prismatic joint. I've said it before and I'll do it one more time. I just can't stress enough the need to have secondary methods to check the results from SimMechanics, or for that matter, any simulation. It's so easy to introduce errors into a model, especially ones that are more complicated than the one I just did here. Also, I just realized that I never showed any of the reaction force plots. Nuts. Hopefully you'll duplicate this model and can look at these on your own. But what you should see is that the reaction forces at the lower pin are much less than those at the upper pin. That's not a huge surprise. And good luck making any sense of all the strange reaction force oscillations due to those wild motions of the lower pendulum. Well, that's the end, and I hope you'll enjoy bending this example to something even more interesting. And as always, this is Gordon Parker from Michigan Tech, and thanks so much for watching.